Hello students and welcome back. In this video we are going to take a look at topic number 6.3. Start talking a little bit about Riemann sums and definite integral notation, and we're also going to talk about some geometry that we're going to use to find some definite integrals later on today. To introduce this section, let's start talking about upper and lower sums. Just talking about how we can find better approximations for area. And much like the ancient Greeks learned several centuries ago, we can find the areas of geometrically challenging shapes by subdividing them into familiar shapes. The more shapes we use, the better our approximation. A circle, before people knew the area formula for a circle, was a very challenging shape to find the area of. So what the ancient Greeks did is they started dividing it up into triangles. So taking a look at these two circles here, the question you want to ask yourself here is which of these two would give a better approximation for the area of the circle? Clearly the answer would be this one, right? There's a lot less space missing than in this one. There's a lot of space missing on each triangle, okay? So the reason why is because circle 2 has more triangles inside of it, all right? So the more triangles that they would add, the more work they'd have put into it, but the closer their approximation would be. All right, the first semester, we focused on differentiation and finding derivatives, and then how they were used. The second semester here, the second half of calculus, we're going to focus on what's called an integral, okay, or integration. There are two types of integrals, definite integrals and indefinite integrals. A definite integral has bounds on it, all right? So these are called bounds, A and B there, and it represents the area under a curve. An indefinite integral would not have bounds, so these would be gone, and that represents an antiderivative, which is something we'll talk about in a couple lessons from now. We're going to start with a definite integral. All right, so here we have a definite integral. Let's start by talking about what all these things mean. This, which kind of looks like a little skinny s, is called an integral symbol. Okay, just like you learned back in first grade that this means plus or addition, okay? This means integration. A is called your lower bound. B is called your upper bound. F of x is your function, which is going to represent your height. And then dx is basically, it's what variable we are integrating with respect to, but when we're talking about rectangles here and finding area, this is going to be the width of each rectangle that we're going to try to find the area of in our next topic. So to read this out loud, if you were trying to read this to somebody, you would read this as the integral from A to B of f of x dx. Okay, that's how you would read that out loud. And again, that represents the area under f of x and above the x-axis. From A to B. So between x equals A and x equals B. All right, so the next thing we're going to do is how to find an integral on a calculator. We can use this to check all of our answers moving forward when we talk about definite integrals in this chapter and beyond. So first of all, we have example 1. Find the area under the function f of x from x equals 1 to x equals 4. And question A says to write the integral describing this problem. All right, so that's just going to be the integral from 1 to 4 of f of x dx. All right, so now we're trying to sketch a graph of this and shade what we're finding. So what we're going to do is we're going to put 1 and 4 into this equation, get back our y values, and draw a graph of what this would look like. So really it's just a parabola that starts at 0, 3. Well, I shouldn't say starts at, but the vertex is at 0, 3. All right, if we put 1 in for x, we would get 1 comma 3.5. So right about there. And if we put 4 in, we would get 1/2 of 16, which is 8, plus 3, which is 11. So somewhere about there. All right, so again, it's just going to be a parabola that looks something like that. All right, this is going to be 4 comma 11 and 1/2 comma 3.5. All right, so we are trying to find the area shaded right there. It's not any shape that we know from geometry. It's not a square, it's not a circle, it's not a triangle. It's close to a trapezoid. So we could estimate it using an area of a trapezoid, but it's not perfect. But if we have a calculator can do this for us. Okay? So in this area here, feel free to write down whatever you feel is necessary here. What we're going to do is we're going to go to our calculator. All right, and we're going to go to our home screen, and we're going to type in, we're going to go to math. And number 9 says FNINT, which is function integration. Okay, so hit number 9, and it should bring up something that looks like this. We want to go from 1 to 4. Type in the function here, so go 0.5x squared plus 3 dx. And if we hit enter there, we should get 19.5, it looks like. So our area is 19.5 under that curve. Okay, so the calculator can give us a nice exact not an approximation of this, a nice exact answer of this. But again, we could have used a trapezoid. If we didn't have this calculator right now, we could have used a trapezoid to approximate our answers. Okay, and that's something we'll talk about in our next topic from there. So example 2 says evaluate the following definite integral using your calculator. So math number 9, again, we're going to go from -2 to 1 of 2x dx. And it looks like we get -3. So the integral from -2 to 1 of 2x dx is equal to -3. All right, so we haven't really talked about a negative answer yet. Negative just means that there's going to be more area underneath the x-axis than above the x-axis. That's something else that we'll talk about much more in depth as we move forward in this chapter. Okay, example 3 says to set up a definite integral that would calculate the area of each region below. So for the first one here, we are going to do an integral from x equals 0 to x equals 1, 2, 3, 4, 5. So from 0 to 5. Of the function, the height of the function here is just a horizontal line, so it's just y equals 3. So 3 dx. That's it. Okay, we don't need to do anything else with that. It just says to set up the definite integral, and that's it. Could we find the area of that without using any calculus? Absolutely. It's just a square or a rectangle. So we should actually know what the answer to this is, but we'll talk more about that on the next slide. Here, because the height isn't just one function, we're going to have to do two separate functions here, two separate integrals. So the first integral is going to go from -4 to 0, right? So -4 to 0. And our second integral is going to go from 0 to 4. And the first height is this line right here. So it has a slope of 1 and a y-intercept of 4. So that would just be 1x plus 4 dx. And our second height is this line here has a slope of -1 and a y-intercept of 4. So -x plus 4 dx. And again, we could find that integral pretty easily using geometry because it's just a triangle. So we know what that area would be. But we'll focus on that in our next slide right here. So number 4 says to sketch and shade the region whose area is given by the definite integral, and then we're going to use geometry to find the area. All right. So the first one here says -1 to 4 of 3 dx. So all we're going to do is plot y equals 3 between -1 and 4. So -1 comma 3 and 4 comma 3, and it's just a horizontal line between them. This is something we should be able to find the area of very easily because all it is a rectangle. All right, so our area here is just the height, which is 3, times the length of this, which is 5, or 15. So this integral would be equal to 15 units. Letter B, 2x plus 5 from negative 2 to 0. All right, so if we put negative 2 in there, we would get negative 4 plus 5, which is 1. If we put 0 in there, we would get 0 plus 5, which is 5. And it's just a line, so a slope of 2, our graph would look like this. So we're trying to find this area right here, which is just a trapezoid. So our area would be 1/2. The height of the trapezoid would be 2. And the bases are 1 and 5. And that would just be 6. So our integral would equal 6. Question C. If you don't recognize what shape this is, just start plotting some points, but hopefully you recognize that this is just the top half of a circle with radius 3. So if we put negative 3 in, or positive 3 in, we would get 0 back. If we put 0 in, we would get root 9, which is 3 back. And since this is a positive here, it's just this top half of this circle. Okay, so the area of a circle form is just pi r squared, right? But since this is a half of a circle, it's going to be pi r squared over 2. So our area is going to be pi r squared over 2, which is just 9 pi over 2. And the last one here, again, if you don't know what this looks like, you just start plotting x's, picking x's and getting y's back and plotting those. So for example, if we put negative 1 in, it'd be 1 minus 1, which is 0. If you put 1 in, it'd be 1. If you put 0 in, it'd be 1 minus 0, which is 1. And if you put 1 in, you would get 1 minus 1, which is also 0. So we're looking at a graph that looks like this. It's just a triangle. So our area would be 1/2 base, which is 2, height times 1, and our area would be 1. All right, and we can double check all of these using the calculator method that we just learned a couple slides ago as well. We should have all the same answers back. All right, now on our last slide, we're looking at a pretty crazy looking graph, but it's going to be a bunch of shapes that we know from our geometry days. Given the graph of f of x below, find a solution to each of the following different integrals. Use the provided graphs to resketch a graph if needed of the function depicted in each integrand. All right, we're probably not going to graph each one separate. We'll just kind of highlight each one as we go through it. So the first one says from -6 to -2. Okay, that's just this shape right here, which is just a semicircle. So our area is going to be pi r squared over 2, which is 4 pi over 2, or 2 pi. For B, we have -2 to 0. -2 to 0. So that's this triangle right here. All right, our area is going to be 1/2 times the base times the height, which is 1. For letter C, from 0 to 4, so from 0 to 4. Now you could do this in two different ways. You can do a rectangle and then that little triangle there, or you can just do a trapezoid once and be done. So we're going to have area, I'm going to do a trapezoid. 1/2, the height is just 1, and the bases are 4 and 3. So it's 1/2 times 7, or 7/2. D, we're going to go from 4 to 6, so from 4 to 6. Okay, so there's two ways to think about this. We can do, it's a triangle, so we can do area equals 1/2, base, which is 2, and then height, which is 2. And then you got to remember that this is below the x-axis, so we got to make it negative. So 1/2 times 2 would would be 2, but since it's below the x-axis, it's negative. The other way to think about it is the height is negative 2. So we could just make this negative 2. Either way, our answer should be negative 2 for this problem. Letter E, from negative 6 to 6. So from negative 6 to 6. All right, now there's a special way of doing this that we haven't technically learned yet, but we're going to learn it very soon. But let's talk about it now. Basically, to get negative 6 to 6, since this is not one special shape, what we're going to do is add up this shape plus this shape plus this shape plus this shape. Right? And we've already found those 4 integrals right here. So really what we're doing is we're going to do the integral from negative 6 to negative 2 of f of x dx plus the integral of negative 2 to 0 of f of x dx plus the integral from 0 to 4 of f of x dx plus the integral from 4 to 6 of f of x dx. Because those 4 we've already found right here. So our answer is going to be 2 pi plus 1 plus 7 halves minus 2. Okay, so that would be 2 pi, and then 1 minus 2 is negative 1, and then negative 1 plus 7 halves is 5 halves. So 2 pi plus 5 over 2. And finally for f, so there's another thing that we haven't technically learned yet, but we're going to talk about it in the next topic, so let's talk about it now, where we can break up an integral into something like this. So 0 to 4 of f of x dx plus 0 to 4 of 2 dx. Just like when we broke up derivatives in our first semester, we can break up integrals in our second semester. So 0 to 4, I believe we've already found that answer. We sure did. It's right here. So that would be 7 halves plus. And the integral from 0 to 4 of 2, well, let's take a look at what that graph would look like. That is just going to be a rectangle with height 2, and width 4. So 2 times 4, which is 8. So we have 3 halves plus 8, which would be 3 halves plus 16 halves, or 19 over 2. All right, so those last 2 problems are a little bit of a preview of where we're headed soon. These are a couple things we're going to learn in the very near future, but it's good practice to start putting them into play right now here. That'll do it for our look into topic 6.3. Thank you very much for looking into this video, everyone, today, and we'll see you again soon.